Alright, we're going to continue with section 14.5 in this video, and we're going to work some exercises from the textbook. So we're on page 943, and we're going to start with number 16, which says, in exercises 14 through 18, express the triple integral as an iterated integral in cylindrical coordinates, and then evaluate it. And we are giving the triple integral over d of y squared dv, where d is the solid region common to the cylinder x squared plus y squared equals 1, and the sphere x squared plus y squared plus z squared equals 4. So it said common to this, and so common to this cylinder and that sphere. So what do we mean by common to? So just because of the wording, I'm going to sketch this in 3 dimensions. So we have a sphere, with radius 2 centered at the origin, and then, so we'll just do a rough sketch of it. So we have the sphere there, and then we have a cylinder with radius 1 centered at the origin as well, that would cut through this sphere. So they said common to this and this, meaning that the region that we're considering has to be inside of both of them, not inside of just one or the other. And we did a problem that was somewhat similar to this, but we were considering the region that was inside of the sphere but outside of the cylinder. Now we have to be inside of both of them, so we're considering this region right there. So kind of like before, the example I gave was if you stick a straw through an orange. Before we were looking at the part that was outside the straw. Now we're looking at the part of the orange that is inside of the straw right there, and that's the region over which we're integrating. So our region D is this part right here. So now we still are going to do our usual top, bottom, and sides, even though we're working with cylindrical coordinates. So we'll start off in a familiar rectangular coordinate realm, which is where they started us off, and then we'll transition to cylindrical coordinates. So our top, and I'll sketch the two-dimensional aspect of this, which is just going to be a circle in the XY plane, or a disc in the XY plane, after we set up everything else from our bounds. So remember, top, bottom, sides here for a triple integral is all bounds. None of it is integrand. So bounds, the top. So the top here is going to be just that portion of the sphere. Now we're going to put the entire equation of the sphere, but we'll restrict it to this when we address our sides. So our top is going to be equal to z equals the square root of 4 minus x squared minus y squared. And then our bottom is going to be down here. We're going to write the whole thing, but we'll restrict it to this when we handle our sides again. So the bottom is z equals negative square root of 4 minus x squared minus y squared. And then our quote-unquote sides, actually let's leave some before I do sides, because I'm going to convert these now. I was going to convert them all together, we'll run out of space. So let's go ahead and convert to cylindrical now. So yes, z stays the same thing, but x's and y's cannot be in there, so we need to get rid of those. So this ends up being z equals the square root of 4 minus r squared. And this ends up being z equals negative square root of 4 minus r squared. So now we've switched to rewriting this in cylindrical coordinates. And now our sides, so our sides will be given by x squared plus y squared equals 1, the sides of this cylinder. So x squared plus y squared equals 1. But remember, we're going to fill this. We're going to fill in the cylinder or fill in the circle. So this, let's just sketch that portion, that sides portion in the XY plane. Oops. So we sketch that in the XY plane. Just end up with a circle of radius 1 centered at the origin. Or a disk, actually. So we're still just taking this solid region and smashing it into the XY plane. And this is what that would look like. But remember, we don't want things in terms of X and Y when we work with cylindrical coordinates. We're basically looking at this now in polar coordinates. And in polar coordinates, this is our radius. Varies from 0 all the way out to 1. And our theta goes from 0 all the way to 2 pi. All right, so now we can go ahead and set up our iterated integral. So we have, since we're doing this for the first time, let me write out the d. So d equals the set of points r, theta, z, such that r varies between 0 and 1. Or actually, yeah, we'll do it this way. I was going to do it theta first because that's what we tend to do first, but I just put it in the same order as him right here. No, actually I won't, because theta is the one that tends to always be your constant. So theta varies between 0 and 2 pi, and I want to maintain that order of constant, function of one variable to function of one variable, and then function of two variables to function of two variables. So regardless of what the order that's in. And then r is from 0 to 1. And then z goes between negative root 4 minus r squared and root 4 minus r squared. And root 4 minus r squared. So that's our region D. And now we can set up our iterated integral, which would be the integral from 0 to 2 pi, and then from 0 to 1, and then from negative square root of 4 minus r squared to positive square root of 4 minus r squared. And then we have to make sure we don't forget about our integrand. Our integrand was, now if we were just asked to find the volume of this thing, then our integrand would be 1, but we were given our integrand as y squared. So what we're doing here is we need to convert to cylindrical coordinates, and y in cylindrical coordinates is r sine theta. So our integrand becomes r squared sine squared theta. And remember, when you do cylindrical coordinates, you need that additional r back there at the back. And then these are z's, so that's dz. These are r's, so that's dr. And these are thetas, so that's d theta. Now, for sake of time, I'm not going to go over integrating this in the video, so you all can attempt to integrate it. And if you get stuck on anything, you can ask me, and I will help you work through it. Or you can ask, you can ask me during a problem session, or you can ask me like via email or discussion. I'll have to work through it. It was going to require a U substitution and I think a one trig identity. All right, so next, let's look at number 18. number 18 says, that's the same directions, and they give us for this one. So 18, they give us the triple integral over d of yz. dv, where d is the solid region in the first octant bounded by the sphere x squared plus y squared plus z squared equals 1, the circular cylinder r equals cosine theta, and the planes y equals 0 and z equals 0. Some of this is redundant information. Those planes, we're already in the first octant, so they didn't really need to give us those. So let's do the same thing that we did before, set up our bounds. And before we sketch our picture, we're just going to write out what they gave us, and then we'll sketch, because I'm not going to sketch the three-dimensional picture here. I'll try to avoid that because we shouldn't need to. I'll sketch on an occasion where it may be kind of confusing what our region looks like. So our bounds, let's see, the top is, okay, so it tells us it's a sphere and a cylinder. So it's similar to the last problem, but this cylinder that we have here is not centered at the origin. So our top, and I should have done this on the last problem, but remember top is going to be your F2. So you kind of know how to set up your region D. It'll make it easier if I just label it the top, which is our F2, or F sub 2, is given by Z equals, because we're in the first octant, so we're going to be looking at the positive part of that sphere. So Z equals the square root of 1 minus x squared minus y squared. And we're going to convert this to cylindrical coordinates. The bottom is just z equals 0. So this is z equals the square root of 1 minus r squared. The bottom is your F1. That was z equals 0. There's nothing we have to do there conversion wise. Then our sides are, so the sides, they gave us the coordinate planes, as well as what we're going to do is look at when this sphere intersects the cylinder that they gave us. So they gave us r equals cosine theta. All right, so first I'm going to look at, let's do it this way. We'll say, let's just put r equals cosine theta. They gave us y equals 0. And they gave us that x equals 0. They also gave us that we were in the first octant, so that's where the x equals 0 is coming from. So, but what I'm going to write this as is when z equals 0, we'll look at this. So the xy plane, since we're in the first octant. So when z equals 0, so we take z equals 0 and we put it in here, and we're going to get x squared plus y squared equals 1. This is that what we've done in the past when we intersect this and this. This is the intersection part right here. So we'll just label that as such. Intersection of that with that. All right, so now let's sketch our, let's sketch the sides. So we're in the first octant. First octant means that your x, y, and z are all greater than or equal to 0. But we're just working that when we reduce that, to 2 dimensions, that just puts us in the first quadrant. So we're going to have a quarter circle. And this is x squared plus y squared equals 1. And we're going to have r equals cosine theta. So we've gone over that a couple of times, but I'll do it again just so we know. And then eventually you'll kind of recognize what that is without having to go through much effort. So r equals cosine theta is in polar coordinates right now, or cylindrical coordinates, whichever way you want to look at it, but that may not be familiar to us. So we'll translate back to rectangular. So this is r is the same as the square root of x squared plus y squared equals cosine of theta is the same as x over r, but r is the square root of x squared plus y squared. So the square root of x squared plus y squared, then multiply both sides by the square root of x squared plus y squared. We get x squared plus y squared equals x. Take this x, move it over to the left. X squared minus x plus y squared equals 0. And then if we complete the square with the x terms, we're going to end up with x minus whatever half, well, x plus 1/2 of this. So 1/2 of -1 is -1/2. So x plus -1/2 quantity squared plus y squared, and then this thing squared gets added over here. So we know now that this is a circle of radius 1/2 centered at 1/2, 0. So we'll put our 1/2 right here. And so that's going to look like that. So now it's a matter of what portion of this. So say we're bounded by the coordinate axes. So there are a couple of bounded regions we could shade in. We could shade in this region, or we could shade in this region. And we need to figure out which of those regions we're shading in. But this right here helps with that. Y equals 0. If y equals 0 is one of our bounds, then that tells us that we're shading in this region down here. Which tells me I actually did not need this for the side, so we'll just make a little note to ourselves. Didn't need for sides. And let me see if there's another place you could have figured that out from the reading. The solid region, the first octave bounded by the sphere and the cylinder. So the only other way you could figure this out is if you sketched it in 3 dimensions. So if you sketched it in 3 dimensions, then now it will be that same kind of straw through an orange thing, but the only thing is now the straw is not being pushed through the center of the orange, it's being pushed through the edge of the orange. So, and the sphere only comes into play, the side of the sphere is not really coming into play. It's going to be the top. The sphere is going to be closing off the portion at the top of the straw and at the bottom of the straw. So that will be using that rationale, or that visualization may help to you realize without this sketch, or without that right there, to see that we really don't need that part right there for our bounds, for our side bounds, of course. All right, so now let's see, we have everything we need to set up our region D. So this is our region. This would be our 2-dimensional region R, is what we would normally call that in. But really what we want is our region D. But we're going to use this. What do lowercase r and theta vary between for this? And then Z, we already know, varies between Z equals 0 and Z equals the square root of 1 minus r squared. So what is our region D? D equals the set of points R theta Z, such that R here, yeah, we've done this, we've seen this a couple of times, but what does R vary between, what does theta vary between? So we're going to do theta first for this. So R equals cosine theta. Our theta here is going to vary between, now if we had the full circle here, then theta would vary between the negative y-axis, so negative pi over 2 and pi over 2. So here, because we only have half of that, this is going to vary between 0 and pi over 2. So remember, if you want to figure out the whole thing, the entire circle, when it's cosine of theta greater than or equal to 0, it's between negative pi over 2 and pi over 2. That'll give us full circle, but we only want half of the circle. So we don't want the first half, we want the second half of the circle. So that will go from 0 up to pi over 2. And then our radius, what does our radius vary between? Remember, your radius is the distance from the origin. So the radius here varies between, so we know right there that the radius is 1 right there, but we're not going to end up using any constant values because the radius changes. So with this theta equals 0, it's 1. With this theta, it's something else. With this theta, is something else. It's our distance from the origin. And as theta changes, that distance from the origin changes. So we know that our radius is a function of theta, which we have that right here, but I'm just kind of using the picture. The smallest our radius is constantly 0. And then the largest it is governed by that curve, cosine of theta. And then lastly, our z's vary between 0 and the square root of 1 minus r squared. All right, so now we're ready to set up our iterated integral. And it is the triple integral over d of yz is what we were doing. So we're going from 0 to pi over 2. And then from 0 to cosine of theta. And from 0 up to the square root of 1 minus r squared. And our integral was yz. Remember, y is r sine theta. Z is z, so we don't change anything there. And then that times that r, that comes with cylindrical coordinates. And then these are z's, so that's dz. These are r's, so that's dr. And these are thetas, so that's d theta. And same thing, I'll stop there with that one. So you can go through the evaluation after this point, but I want to make sure we go through probably the most troublesome part of most of these problems is the setup. All right, so I'll stop this video here and then I'll do some more 14.5 examples in the next video.